It's a pleasure to be here, albeit remotely. I will probably be sad not attending the visit later on down in downtown Santiago. But in the meantime, the task at hand for me is to give you a brief overview of the activities of Working Group 3 within the Milky Way Gaia cost action. This is the very brief summary of the objectives of the working group, which are focused essentially on the science of solar system and exoplanetary systems. The main tasks are subdivided into three sub-working groups, which are outlined here. One is essentially focused on the solar system, one on detection and characterization of exoplanets, and the third one on the investigation of exoplanetary environments, including the connection to stellar properties. There have been some relevant activities in the working group in the last, since the beginning of the action, with a hiatus of about 2 years, as you certainly know, due to the pandemic. 4 workshops are listed here. 3 workshops and 1 school are listed here. 2 that have already been essentially completed, 1 that is upcoming, and the last one that is coming up also rather soon. The first one to be happening was the Porto workshop in November 2019, focuses on the science of exoplanets, essentially in the wake of the first Gaia data releases. In this case, we focused on a few relevant aspects of exoplanetary science with the expectations from the Gaia exoplanet yield and investigation of the various synergies that will be potentially in place between Gaia astrometry and a variety of other detection techniques, both from the ground and in space. And then there were also other discussions and investigations specifically on architectural properties of exoplanetary systems and the star-planet connection. This was a rather successful workshop with exceeding the initially expected number of 30 people or so, with a variety of participants across Europe and even the US, and a reasonable, although maybe not entirely optimal, gender balance between the participants. The second workshop performed last year on exoplanetary, planetary science, solar system science, was focused on investigations of asteroids and comets. This was an entirely online event, only exclusively upon invitation, with 25 participants. It was held online from the Helsinki University, and it focused on 2 main areas. Asteroid science, in terms of the physical characterization, taxonomy, using particularly advanced tools, investigation of near-Earth objects, and general constraints on the size distribution of the asteroid families. In terms of cometary science, we discussed photometric and polarimetric studies, in particular applied to understand the planetesimal formation in the first place. And there were also issues addressing specifically the thermophysics of the constituents of the comets, in particular dust particles. In the immediate future, we have just coming up a Working Group 3 workshop to be held at the Aarhus University in Denmark. This will be focused on the investigations of stellar parameters and astroseismology in the area of Gaia, so essentially taking advantage of the wealth of information that comes from successive Gaia data releases. You see here the list of relevant invited speakers. And last but not the least, there is also going to be a school in September, this one, in the middle of September. This will focus on astrostatistics as applied to exoplanetary science. You see here the list of speakers that essentially are people expert in astrometry, radial velocity, and transits, which are the latter 2 being the most successful detection techniques in the field. This is a bit of advertisement. You can still register until the middle of June, and this is the list of 5 days in which the school will unfold with a list of topics that will essentially be a combination of lectures from the lecturers that you have seen before and hands-on sessions focused on handling of orbital solutions, for example, and characterization measurements both with astrometry, radio velocity, and transit work. Now, let's get a bit more in the detail of the activities of the 3 subtasks that I have indicated. Working group 3A is the one that focuses on solar system science, as a specific focus on the sub list of topics that I show here, with a particular, let's say, I would like to particularly underline and stress the studies of near-Earth asteroids and main belt asteroids for the purpose of very high precision orbit determination and mass measurements. There is also important activity in terms of measurements of diameters of a large number of objects to study their shapes and densities. And there is also ongoing work in terms of, in particular, photometric studies to do taxonomy and to study shape, orientation, and rotation of a large number of objects. A few snippets of ongoing work. Some is focused on the study of stellar occultations by solar system objects, in particular trans-Neptunian objects. These are very, let's say, very sensitive measurements that specifically exploit the information accounts from successive Gaia data releases to pinpoint extremely precisely the star positions that are actually going to be the main targets of the occultations. Other measurements that are beginning to be the matter of important studies are the ones connected to a very subtle effect in the solar system, which is called the Yarkovsky effect. This effect essentially translates into a change in the center axis of the orbit and the obliquity of a specific solar system minor body when it is under the influence of radiation pressure from the sun. And there are beginning, essentially, initial exploratory studies of the combination of Gaia astrometry with long-term information from ground-based surveys of these objects to pinpoint actually very small variations as a function of time in the orbital elements, in particular in the orbital center axis. This is a fundamental information, particularly when it applies to evolution studies of these families of orbits of these minor bodies. And finally, there is also spectroscopy that is contributing directly, and more is to come thanks to the upcoming Gaia data release 3 in just a few weeks from now, as you all know. In this case, the activities are focused on the study of the optical spectra in the visible primarily, to investigate essentially the reflectance properties as a function of wavelengths. This way, you can learn about the composition and study in detail some of the aspects related to the evolution of families of collisions that could have occurred in the past. There is more to come in this specific topic by a talk after mine. Working group 3B is the one that focuses explicitly on the characterization of exoplanetary science, of exoplanetary systems with Gaia astrometry, but not only. It has so far focused on 3 main lines of activity. Forecasting the exoplanet yield that we are expecting, taking advantage of the fact that now Gaia is actually most likely to be extended all the way to doubling its initial mission lifetime of 5 years. There is also literature work that has impacted the characterization of companions already known by other detection methods, and to which Gaia astrometry has begun to contribute. And then there is obviously the large amount of expectations from to start with Gaia DR3 release of orbital solutions. The Gaia discovery space is a complex thing to describe to you. I will like to have you focused entirely on the regime of planetary masses and semi-major axes that Gaia can detect. These are the purple curves that you see, upper and lower curves. The solid ones are the ones that we are forecasting be the sensitivity curves for detection of such companions with a 10-year Gaia mission, while the other ones are the ones that apply to a standard nominal 5-year mission lifetime. As you can see, the typical Gaia planet detection domain is that of giant planets with typically the mass of Jupiter or larger, at a couple of astronomical units or so of orbital separation. The key of the expected Gaia contribution to exoplanetary science is the fact that, in principle, Gaia will be sensitive to many stars with sufficient sensitivity to detect planetary companions. And the estimate, thanks to a vast literature that I am listing here, is that Gaia is expected to indeed find maybe as many as over 10,000 new giant planets. And this number, based on the latest estimates for the extended mission, triples, maybe down to 20 to 30,000. Such a large number, indeed, can only translate into an expectation for a fantastic contribution to the study of the statistical properties of this class of companions, and investigating indeed the fine structure of the distributions of the parameters of giant planets, their orbital parameters, the masses, the frequencies, and any correlation that can and certainly is established already between planetary properties and the properties of the stellar host, in particular mass, metallicity, and age. However, as of today, there is no direct information on binarity. Data release 2, which is until data release 3 is what we have been working with, has not directly contributed to detecting binaries by themselves, or planets for that matter. However, it has allowed scientists to use a very clever technique, which is called the proper motion anomaly technique, to actually put constraints on the presence of such companions. This is outlined here, the gist of the methodology. It essentially takes advantage of the fact that if there is orbital motion in the stellar motion observed at very different epochs, this can reflect this can translate into a different value of the instantaneous proper motion measured by a catalog such as the one from the Hipparcos mission with respect to the one determined by the Gaia mission. And this proper motion difference, once it is measured accurately, can tell you about the orbital properties and mass potentially of the companion that is causing it. This technique has been applied to, let's say, probably more than now a dozen or so, or maybe more, systems, typically brown dwarf systems, but in a few cases, like the one that I show here, also very massive planetary companions, already known, for example, detected through direct imaging techniques or radio velocity measurements, and usually the combination of those, to which the inclusion of the two epochs of very high precision proper motion differences at the Gaia and Hipparcos epoch actually tells you something more about the orbital architecture and mass of these objects. This has been an effective method to measure dynamical masses, and one spectacular result that we have obtained recently has been the one that I described here briefly. It pertains to the bright star system Pi Mensa that hosts two planets. One was known through radio velocity work in the past to be a very eccentric, a very supermassive, super Jupiter companion on a long period orbit. And the second one was found recently to transit on a very short period orbit. It's a very small object with a radius of just a couple of Earth radii, orbiting on a very tight orbit, and it's transiting. It was found through the transit technique by the TESS mission. The use of the Gaia proper motion technique applied to the radial velocities and the transit work has allowed to further characterize the system and, in fact, pinpoint the difference in inclination angles between the outer companion, for which now we have a mass estimate and an inclination value, with respect to the orbital arrangement of the transiting object, which we know has an inclination exactly identical to 90 degrees. And the outcome of this study points to a very large difference in inclination, with a relative inclination angle of maybe 50 degrees or larger between the two companions. This is indeed one of the most spectacular applications of this technique. Now, what's to come is Gaia DR3. You may not be able to read very clearly, but I am highlighting here in the list of things that will be released by Gaia DR3, a couple hundred of exoplanetary transit candidates, and very much larger numbers, hundreds of thousands of orbital solutions that will come through the first release of non-single star solutions at the level of Gaia DR3. At the bottom, you also see the numbers pertaining to the spectacular increase of information in terms of studies of solar system objects. As far as exoplanets are concerned, we are definitely expecting something relevant for Gaia DR3. You see in the top left panel the expectation of increasing number in detected giant planetary companions as a function of period when you move from a 5 to a 10-year mission duration. And to give you a first snippet of what is to come, you see as an image of the week published on the main Gaia website, the Gaia orbit for a known supermassive super Jupiter companion known through radial velocity work. The result of the Gaia orbital solution is actually in very good agreement with the radial velocity orbit, and so this is very encouraging for the future studies. But just this morning, we had the pleasure to see more, and this is the summary slide of what has just been published by Panay and collaborators on the discovery of the first two Gaia confirmed transiting planets. These have been dubbed Gaia 1b and Gaia 2b. They orbit moderately bright sun-type stars with 13-11 magnitude or so. You see in the left panels the transit light curves folded to the periods of the objects. Gaia has this very uneven way of sampling objects in the sky through the scanning law, so you cannot expect a very well sampled light curve during transit. But the size of the event, or the magnitude of the event, the depth of the transit is such that even few points in transit are sufficient to clearly detect the event. And this event was followed up with other radial velocity work for mass confirmation, and indeed these two turned out to be moved from candidates through the transit technique to actually confirm planets. And this discovery announcement just came out today in the literature. These are two standard hot Jupiters with periods of just above 3 days, masses around the mass of Jupiter, and radii that are a little bit larger than that of Jupiter, which is known and expected an effect due to the fact that these are mostly gas balls, primarily made of either hydrogen and helium, and so you put them very close to the parent stars, they heat up, and so they are a little bit puffed with respect to the expected radius they would have if they were to be sitting at 5 astronomical units of orbital separation. To conclude, working group 3's activities are focused on planet hosts primarily, and the environment in which planetary systems move. These are three main areas of ongoing work that I'm listing here, focused primarily on the careful determination of properties of the stellar hosts, understanding the galactic environment in which these hosts move as a probe of potential scenarios of exoplanet formation and evolution, and another very interesting aspect is the one that is now, just recently, beginning to attempt to link the local chemistry and the chemistry of the parent stars to the demographics and composition of very small mass and small radius objects. A couple of examples of relevant work applied that, let's say, fits exactly the activities of working group 3C. I summarize here a couple of relevant works that have exploited the information, in particular spectroscopic and astrometric information from Gaia, combine it with long-term spectroscopic surveys from the ground, such as LAMOST, Apogee, and RAVE, for example, to study the kinematics of exoplanet host stars. This is the diagram on the left, and understand essentially the relative fraction, for example, of objects that belong to the thin, the thick, and the halo of our galaxy. There are other studies, the one in the center, that is concentrated on, again, exploitation of the combination of LAMOST and Gaia data to, for example, infer, potentially, maybe not to very high statistical level of confidence, but at least tentatively, the fact that the stars in the disk, or the thick disk, or once we look at the range, seem to correlate with planet multiplicity in different ways. Stars that are a little bit younger seem to have a larger increase in the percentage, the higher the planet multiplicity. And the contrary holds instead if we look at objects with a thick disk, let's say, classification. The last, but not the least, is the diagram on the right. This is a period radius diagram for a planetary sample of recent studies. In this case, the relevant investigation that was performed was to study an extremely important feature in the radius distribution of small size objects. This is called the radius valley. That is known to be in place most likely because of photoevaporation effects that are acting upon these objects for timescales of giga-years, as much as they have been orbiting around the parent stars on very close-in orbits. And this additional study, based on updated planetary radii, thanks to the improved measurements of the stellar parameters from Gaia, in particular the availability of exquisitely precise parallaxes, has allowed to improve the characterization of this feature. To conclude, and to give also a heads up to yet another talk that is coming after mine, is the issue of the diversity of rocky planet composition when we compare it with the chemistry of the host stars. And this is an example, and the next talk will get more into detail on the fact that if we estimate, for example, the iron fraction, of the interiors of these of a subset of transiting small mass objects, we can correlate it to some extent, at least, with the iron fraction of the planet hosts themselves. Where naively one would expect a very strong correlation, because we would imagine that what the planets are made of traces the initial composition of the protoplanetary disk in which they formed, and this traces the composition of the star.
Alessandro, sorry. Yes. The 5 minutes. All right.
Perfect. And this is my last slide, in fact. I've actually very well in time. And the situation is not that clear. There seems to be a correlation, but the way planets form and the way they evolve in the initial protoplanetary disk most likely has to take care of much more complicated processes that indeed impact the internal composition to a significant extent, such that this direct correlation ends up being smeared. I think I can stop here and take any questions.
Okay, thank you very much. Perfect timing, absolutely.
Thank you.
Is there any question in the audience? It's been most interesting, this talk. Do you have any question, curiosity, and online? Do we have any? There's one.
Yes, I would like to know, in Gaia data release 3, there will be solution for binaries, orbital solution for binaries. Those orbital solutions are based solely on Gaia data, or you will be taking into account ground-based observations?
No, yes, clearly. The data release 3 will produce orbital solutions based entirely on Gaia information. These will come in 3 flavors. There will be eclipsing binary solutions, all the way down to very small depth of the eclipses, which will be the sample of planetary transit candidates. There will be spectroscopic binary solutions, radio velocity based, and there will be astrometric binary solutions. The astrometric binary solutions and the radio velocity spectroscopic solutions will come in different flavors. We will have full orbits for orbital periods that are approximately more or less 3 years or so, not much longer than the time span of the Gaia observations used for Gaia data release 3. And then there will be also a large element of information, close to 1 million orbits maybe, close to 1 million solutions, that will be called instead acceleration solutions. Those will essentially provide preliminary information on the presence of very long period companions that with just 3 years of Gaia data is not possible to entirely characterize.
Okay, thank you. No more questions? And we don't have any online, right? Okay. Shall we thank our speaker again?
Thank you. Thank you to you.